Today we're going to learn about the derivative. Now in calculus, the derivative is the basis of everything you learn, so it's really important that we understand this before we move on to other things. So the first thing you need to learn about the derivative is that it's the same thing as the instantaneous rate of change, or the slope. And we're going to use this fact so that we can find the limit definition of a derivative. So we know from algebra that the slope of a line is given by the change in y over the change in x. And we know that the slope of a function is given by the slope of the secant line on that function between 2 points. Now the derivative represents the slope at one single point on a function. So that's going to be given by the tangent line at that one point. And these two are related in a fairly simple way. So if we move y closer and closer to x, these lines that I'm drawing are going to more closely approximate this tangent line. So we're seeing that the secant line slowly turns down until it's fairly close to the tangent line. And so the formula for the derivative is going to model this process algebraically. So we saw in the graphical representation of the derivative that as we move x and y closer together in the x-axis, the secant line more closely approximates the tangent line. And the tangent line is what we want to have the derivative. So we're changing the distance between y and x in the x-axis, which is the same as this value here. So let's just call that value h to make it a little easier. And we'll also change it up here just so we can see it in the formula. So h represents the distance between y and x in the x-axis. So what we want to do is, since we got rid of the y down here, we also want to get rid of the y up here. So we're going to do that using this equation right here. Since h equals y minus x, all we have to do is add x over, and we get x plus h equals y. And so we'll plug this value in up here. Now this equation is getting really close to the definition of a derivative. We just need to look at the fact that when we looked at the graphical representation, we only moved x and y together a few times. And that secant line got closer and closer to the tangent line, but it never really got there. We're actually going to have to move x and y infinitely close together in order to obtain the best approximation of the tangent line. And the way we're going to do that is we're going to use the limit. So we want to take the limit as the distance between x and y, which is h, goes to 0. So this is actually the definition of a derivative. It's the slope of the secant line of 2 points that are infinitely close together. So it's essentially the slope of the function at one point. So now that we have the definition of a derivative, which is the limit as h approaches 0 of f of x plus h minus f of x over h, we can use it to find the derivative of different functions. So we're going to do an example real quick of the function x squared, and we want to find the derivative when x equals 2. So we're going to start by just plugging into this equation, and we'll get the limit as h approaches 0 of x plus h squared minus x squared over h. So what we want to do with this is simplify it as much as we can to try and get rid of this h on the bottom. Because right now, if we plug in h directly, we'll get a 0 on the bottom, and we know that that can't happen. So we're going to try and get rid of that by simplifying this top part. So to start, we'll see that this is equal to the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared over h. And we get that just by multiplying this out. So we see here that these x squareds already cancel out. And now we're left with 2xh plus h squared over h. So we can actually factor out an h from the top and get rid of the one on the bottom too. So now we're left with the limit as h approaches 0 of 2x plus h. Now because of this limit, this h goes to 0. So this equals 2x. Now we're trying to find the derivative at x equals 2. So we can just plug that in, and this equals 4. So now we know pretty much everything there is to know about the limit definition of a derivative. We have the formula, and we know how to apply it to a function.